Baozi Training Leetcode solution. If you want the best mock interview experience in North America, feel free to check us out at baozitraining.org. We're here to help you land your next offer. Moreover, if you can read Chinese, we also feel free to subscribe to our WeChat channel, where we every week will publish an article, and also we will, give you some exclusive information about the tech industry and the job offers. So feel free to subscribe. Okay, so today we're going to talk about this problem, which is a relatively easy problem called reverse bits. So essentially, the problem is giving you a, let's say, an integer. So in this case, 32 bits unsigned integer. I think here it calls out the Java because Java doesn't really have an unsigned. It has only signed integer. And yes, so essentially, if you're not familiar with the two's complement notion, just take a look. But just by looking at this problem, the way it was implemented is just give you the 32 bits. You just want to reverse it. So one way is essentially you can directly use integer.reverse. You can check the Java doc. It's exactly what this problem needs. However, this is not really suitable for interviews. So what we can do is basically a simple simulation. Essentially, you start from the least significant bits, and then you keep reversing, and then you keep adding them back together, and then you return the results. And then the follow-up question is, how would you optimize this? So one way to optimize this, in my opinion, is, obvious solution is caching. So there are two ways we can cache it. So one way is we can cache all the integers. So there are 32 bits of each integer, and then there are this many. So if you time them together, it's like 16 gigabytes. For a modern server, let's say it has like 120 gigabytes. It's easily, you can cache everything in memory on one single machine. And another way is you can cache it, let's say, instead of the entire thing, you can cache it a 8-bit, which is 1 byte. So this results so that we can divide this into 4 bytes and then reverse them together. And then for each of the byte, we can keep a cache. So the memory footprint of this method is significantly small. It's like 256 bytes compared to 16 gigabytes. So I also implement a way that we can reverse with cache. So essentially keep a map. Each key is byte, the value is the integer. And then first of all, you need to divide this integer 32 bits into 4 bytes. And then for each of those, you have to reverse it. How do you reverse a byte? So this is a separate method how we can reverse a byte. It's the same code template. And once you reverse it, so you also need to keep adding them together, and then you return the result. If you are curious, you can also check how Java SDK actually implement this method. So as long as you see it here, so it's like a purely bit manipulation. Regardless, you have to, for example, the time complexity, right? So regardless, you have to touch every bit once. So that gives you basically in terms of ON time complexity, which ends the number of the bit. But in Java, this is very hard to read, and then you see the comment. So HD figure 7.1, HD means hacker delight. So I have the book link here as well. So figure 7.1, that's the section. So this method is actually, it still kind of touched the bit, but I think it also utilizes the kind of like the memory cache registry that those, for example, like they always use 555 instead of here. The most efficient way is actually use A, which is 10. I'll explain this later. And also note here, so this also has the right shift, which is instead of 2 larger size, this has 3 because this is keeping the bits, the first significant bits. So the way that this algorithm works, or if you check it here, this works is, so essentially, we look at it here, but this is actually the original one. So it's a divide and conquer kind of notion. So let's say this is A, B, C, D, E, F, G. So this is like 8. Let's say each of them represents a hex number. So there's a 32 bits. So each of them, there's 8 of them. So each represents 4 bits. So the way it works is it's swapping each of the digit first, each of the bit first. So, sorry, forget about whether it's a 32-bit. Let's just say this is each of them is a bit. So first thing you do is you swap A and B, C and D, divide and conquer. So after that is B, A, D, C, F, E, H, G. And then you treat those two together as one, and then you swap them, and then you see D, C, B, A, H, G, F, E. And then you treat these four together. So if each of them is a bit, let's say this is 0, 0, 0, 1, 0, 1, 0, 1, something like that, and then this is now 4 bits, right? And then you swap these two together, so you get like HG, FE, DC, BA. So now this is exactly the reverse of the original string. So the reason it uses, let's say it uses 5 first is because 5 is 0, 1, 0, 1, and A is 110, 110. So and then later it uses a 3, which is 0, 0, 0, 1, 1, and then the counterpart I think is C, is 1, 1, 0, 0. So this means, they are using this trick that once you end this number, let's say if you have a number represented as a bit here, once you end them and then right shift by 1, and then you use the counter bit 0, 1, 0, 1, 0, and then you end, and then you right shift by 1, it's exactly reversed. So if you look at this example 0, 0, 1, you end them together, you get here, and then you left shift 1 bit is 0, 0, 1, 0. Here, same thing. If you end these two numbers 0, 0, 1, 1 and 1, 0, 1, 0, you get this one, and then you right shift is like this, and then you OR these two numbers together, which is 0, 0, 1, 1. I think I missed something. Okay, sorry. I was talking, forget about this part. So this is, I think, is from this book. I read it from the section 5.1, which is where we do they call it a population count, kind of using one integer, each of the bit, they end them together. But for this one, you can just think about the idea is divide them into like, you're just trying to swap the smallest integer, every bit, and then you swap it later on. So that results in the code like 7.1. Where is it? Here, this is the 7.1 part. So you swap each of the digit, and then later you shift them, and then you end the entire thing, and then return the x. Anyways, it's just for you if you're interested. And I think honestly, this book was written back in the 2000s, where memory is really limited. But for now, probably doesn't even need this kind of like thing if we have enough compute power. So just FYI. Alright, that's all. Thank you very much. Thanks guys for watching. A train of thought earlier, or short-circuited, getting too old. So while I was explaining like 0011 and why it ended up to be like still 0011. Yeah, so the problem, so I was lost earlier. So basically I'm just trying to follow up with this algorithm, right? So let's make it simple. Instead of 32-bit, let's just make it only 4-bit. So for, as you can see, for 32-bit you only need to shift it like half, which is 16 bits. So for 4-bit you only need to shift it twice, 2 bits, which is we only need these 2 lines of code, right? So what end up happening is if we have this number, we want to reverse it, and then the end result should be 1100. So how should we do it? First, we do the first line, which is end by 5, left shift by 1, and go away playing. And then we end by 10, which is A, and then right shift by 1. So we end up with these 2 numbers earlier. So what this is doing, so as you can see, this is interchanged, right? So this is basically swapping 0 and 0, 1 and 1. So that's why the end result we get a 0 and 1, 1. So the next step is basically doing it like ended with the 3 and the C, which is 0011 and 1100, right? So if you're doing this same thing, same algorithm, we get these 2 numbers, and then we OR these two numbers, we get 1100. So this is our end result. We successfully reverse these two. And then this normally will be the code you write, but instead Java wrote this is because if you read it here, so a small improvement may result on some machines by using fewer distinct larger constants, because now we have a large constants like 555 and 888 different ones, and doing the large two assignment in a more straightforward way. So this is kind of a reusing the assessment. So it's like end by this number, redshift by 1 is equal to redshift by 1, and then end by the same number. So those are purely some to me it's like a bit magic that is very hard. So this is trying to avoid basic risk instructions on branch free, so that you don't need to, remember in the assembly languages you have to branch one step ahead and then you're doing some kind of move thing. So this is I guess very efficient. So that's why Java directly just copied. Whoever wrote this code just copy paste the code from here. HD figure 7-1. All right, that's it. Hope it's helpful. Hopefully you never get asked these kind of questions in your interviews. Adios, bye.